Okay, following up on the theme of cosmological simulations, I think the field started at a very well-defined point in the 1600s when Newton basically established the system of the world, and he showed that the gravity that affected the moon's orbit around the Earth could explain the tides, it could explain the orbit of moons around Jupiter, that there was a universal law that described our universe, and it in fact is the same physics we use for dark matter with a few corrections at very large scales. So we do simulations to validate our theories by comparing them with observations. And in cosmology, 20 years ago, we were very data poor and theories were not well constrained. But now with satellites like Planck, we have a great deal of data and we can perform very sophisticated comparisons between our theories and observations. So I want to very briefly kind of go through the whole role of simulations. What is Exascale? How do we develop algorithms to take advantage of this hardware? How do we turn that into scientific results? So what's driving computing to Exascale is Moore's law, the fact that every 2 years or so, the cost of a transistor is half as much. So this is just from 1990 to the present. You went from 1 million transistors on a device to something like 10 billion. So Exascale is going to be about another, add about 8 years onto this curve, and we will be at Exascale in terms of the transistors needed to do that. And these benchmarks are actually measuring the speed of calculating gravity in an inner loop on all of these processors, which has been tuned specifically for each individual processor to do as well as that processor can do. And one point to take from this, you know, back in 1990, the Cray YMP was the supercomputer, and these microprocessors were basically little things that you put in home computers to run spreadsheets. And the fact that YMPs went away was due to the fact that it was hard to program these with their long vectors. You couldn't write a simple program that got good performance. You needed experts in writing software to get any sort of performance at all, whereas a microprocessor was relatively straightforward to program and get good performance. But now we've come full circle. We're back now at GPUs with very long vectors, very difficult to program, and we've got the vector problem again, on top of being massively parallel and having other types of parallelism and threading. But you can see just by measuring the number of particles in large cosmological simulations over time, the scale has gone. In 1970, this was a simulation done by Jim Peebles, who visited Los Alamos to take advantage of the supercomputers there, with a few hundred particles. Now we have multiple codes at the trillion particle scale. And the n-body problem itself has shown up a lot of times as kind of the poster child for the very highest performance computing, winning the Gordon Bell Prize with just 2 years ago, Ishiyama with a tree PM code won the prize. Our group has run it in the past a couple of times. Grape special purpose hardware using n-squared calculations. So you can see this dramatic increase in scale, but I want to call out the fact that if you put a bar graph on here with the number of citations derived from each of these simulations, some of them, which were extremely large for their time, were virtually worthless scientifically. You know, something like a single paper from a state-of-the-art simulation because it had a bad random number generator. The most highly cited point on this graph is right here. The Millennium 2 simulation has generated over 1,000 citations. So we have this explosion in these very large simulations at very large scale, but it's taking a very long time to get scientific data out of them. So Millennium XXL, the first preprint was almost 2 years after the completion of the simulation, and that's just much too long to do science that way. We have to turn large simulations to scientific results more quickly, and that requires rethinking how we approach these problems. So looking at the whole scale of limiters, this is just to point out, to do a floating point operation, it has to measure its cost in a reasonable way, and it's something like 10 to the minus $17 to do a single floating point operation right now. If you look at the other end of this table, if you want one line of software, that costs $10, because you have to pay people to do that. You can't scale that process very well. So this is the important cost in everything we're talking about in approaching exascale. And one of the reasons for that is, some of the things we work with scale very well. You could take advantage of network effects. So this is Metcalfes Law, which he pointed out that if you have a network, its value scales as the square of the number of communicating entities. So if you have lots of data sets, if you can compare them to each other, each data set becomes worth more. But things like human minds don't particularly scale very well. The communication is difficult. If you think of these as university departments, how hard is it to get a statistician and a cosmologist and a mathematician and a computer scientist in the same room working on the same problem? If you have a graduate student who does fantastic work in computational science, but he is in a physics department, that doesn't pay off nearly as well as staying in the stovepipes of these organizations. And to do exascale, we need very interdisciplinary teams. So supercomputing really is fundamentally interdisciplinary. And one of the things that exascale is doing is the fact that we have simulations that we've validated in the past. As you add more and more particles, you're suppressing the fundamental noise limits to the point where you now have systematic effects showing up that before were masked by the fact you just didn't have enough particles to sample the phase space well. So suddenly you're exposing problems that you need mathematics and statistics to solve, and if you're a scientist trying to solve a particular problem, you either need to go out and create a collaboration with people, which takes years to establish, or you have to become an expert in statistics. If you have a particular routine you need to optimize, who do you call to write vector code for current microprocessors? That's not really a job skill that's easily found in applications from grad students for summer positions at Los Alamos. One of the most valuable skills for science are now also the most valuable skills for places like Google and Yahoo and Facebook. That is what's driving information technology now, and we have to compete with those minds because that is what we need to write the software that does these problems. So the particular codes that I've worked with for 20 years now are based on tree methods doing multiple expansions of gravity. So you convert an n squared problem into an order n log n problem by doing various approximations. And this is a very parallel problem, so the trick is just mapping this to architectures. And one interesting fact I wanted to point out, Andrew Apple was an undergraduate at Princeton, and Jim Peebles was his advisor, and he basically came up with this idea of doing multiple expansions, which was then followed up by both Barnes & Hutt and Green Garden Rockland, and had huge communities develop independently in applied mathematics and astrophysics. but that was his undergraduate thesis, which started this whole branch of algorithms. And Andrew is now the chair of the computer science department at Princeton. So the basic idea is doing expansions of these cells. So the parallel computing aspects are dealing with domain decomposing these and labeling all these cells to keep track of all the work you need to do. So one of the advantages of pure tree codes over tree PM approaches, if you do a Fourier transform code and then tree code at small scales, there's a transition region where you have to fit those together. And it's very difficult to do that at high accuracy while being efficient. You can move this scale out, but then you have much more work to do. So you can see in Springel's original paper, you get errors at 1 or 2%, and this is now measurable in simulations. You can see the effects of this transition region in tree PM codes, which you can avoid because tree codes don't have that particular scale. Tree codes in the past did not perform at all well on large cosmological simulations, but we've recently come up with a way to basically make the machinery work better on cosmological scales by subtracting the background, because a lot of the time was just taken up by calculating forces from things that would largely cancel. So that makes the tree codes competitive with these other algorithms. And then you have to fold in there's been a lot of progress on other aspects of the algorithms over the past 20 years. Improved ways to smooth the forces at small scales, doing symplectic integration. An advantage of not having a fundamentally periodic code is you can do things with vacuum boundary conditions and hierarchical initial conditions more naturally. So this is a comparison between the 2-hot code and Gadget. And if you look here, this is a linear scale. I mean, these are the days of precision cosmology. So anyone who shows you a logarithmic plot is masking where the real information is. So this is 0.5% difference between these codes. And basically turning the error tolerance up and down on the 2-hot code, looking at different ways to smooth things. You can see in these regions, as Anatoly pointed out, depending on the parameters you put into Gadget, you can get different answers. So we can now use these codes to test each other and probe things very sensitively. And one thing I can guarantee is whenever you compare two codes, they are going to differ. So the important question is, do the differences matter? Is it scientifically relevant? And that's one of the tasks that we have to do in this community, is make sure that we are validating the codes against each other. So a recent series of simulations, these are our 69 billion particle simulations, which we worked very hard to show convergence in mass resolution for the mass function. So these 4 different simulations overlap very well at the percent level, where between each of these, the mass of each particle is varying by a factor of 8. So it shows you can run very high resolution and get the right answers. You need to show this to show that your codes are converging. So what we're currently working very hard on is a project this year on Titan at Oak Ridge. We have 80 million CPU hours. We plan to do a number of simulations at the trillion particle scale, and the big challenge is turning that into scientifically useful data. So particularly having Matt and Sam help with integrating the data products coming out of these very large simulations in a way that a postdoc without a lot of parallel computing skills can use those to answer scientific questions. So the real problem at Exascale is not hardware. The hardware will be there. The real problem is software. And this quote from Kernighan is basically, you know, if you write code at the limits of your cleverness, you can't debug it. And the hardware is forcing us into this corner where, you know, to get performance, we're writing code that we have to be very clever, and it's very brittle and breaks very easily. And Dijkstra pointed out, this is in 1972, he's talking about the software crisis by very fast machines. So it's 40 years later, and this is still the problem. Gigantic computers and a gigantic programming problem. So I have from the point where I was a graduate student writing these codes to right now, the codes I've written on the same problem have gotten 1,000,000 times faster. But, you know, what's in here has gotten nowhere near that much better. So the fact that our hardware is producing data at 1,000,000 times the rate it did 20 years ago, we just cannot keep up without fundamentally adjusting the way we write software. So we need better software. We will have a machine around 2022. It will run LinPack at an exaflop. So that's the political exaflop. It runs a useless benchmark at 10 to the 18th floating points per second. So when this machine does something useful depends on us, and we have to start now because it's going to take that long to write software for these machines. So Exascale is not hardware, Exascale is people.